Welcome back. In this last lecture of the course, I will be describing three problems. So let us start with the first problem. The first problem states that in a binary solution system of solvent and polymer, solvent is represented by 1 and polymer by 2, the composition at which the UCST occurs depends on the polymer molecular weight. According to the Flory-Hagens theory, the critical segment fraction is known as 1 plus root r, okay, where r is number of segments. Now, what is being asked is to derive this particular segment fraction. Okay, so let us write down the expression. So, we know that for critical or for incipient instability, we need to find out the first and second derivative of log of activity, or you can replace that also in terms of the activity coefficient, or basically the activity. It is basically originates from the conditions of the GE which we have looked at to earlier. So, let me write the expression of activity based on the Flory-Hagens theory. Okay. So, this is something which you can write. Okay. And this particular question is from the textbook. So, let me try to now use this expression, and then what is the condition for the incipient instability. Okay, this is going to be log or tau ln a 1 by tau phi 1 star pt is going to be 0, and the second derivative okay. So, this is equivalent to state that d ln a1 d phi 2. So, this statement is equivalent, these two statements are equivalent. This okay. Now, if you plug in this expression here, so you should be able to get from here 1 minus phi 2 c minus 1 minus 1 by r minus 2 chi c phi 2 c equal to 0, and this one would be 1 by phi 2 c 2 minus 2 chi c equal to 0. So, using these two expression, one should be able to find out what is phi 2 c. Okay. Phi 2 c and as well as chi c. So, if you solve this, then we obtain phi 2 c as 1 by plus r, and chi c is 1 by 2 1 plus r to the power square. Okay. So, this is a very simple way of solving this problem, where we have just made use of the expression of the activity based on Flory-Hagens theory, and then we use the condition of incipient instability. So, let me now describe the second problem. So, this is question 2 or problem 2. So, let us say in a polymeric solution, it is sometimes convenient to define an activity coefficient as A1 by phi 1. Okay. where A is of course the activity and phi is the volume fraction. 1 represent the volatile component. Okay. So, when phi 1 is small, gamma 1 is written as gamma infinity, and in that case the Flaherty-Huygens theory or equation gives us the following expression. Okay. Where chi is the Flaherty interaction parameter and R is V2 by V1, where V is basically molar volume of the polymer V2 and V1 is for the solvent. And what we are considering is basically R is much greater than 1. Okay. So, this is the statement of the problem. Now, let us consider a specific case. So, let us assume a film of polyvinyl acetate which contains traces of isopropyl alcohol. Okay. Now, for the health reason, the alcohol content of the film must be reduced to a very low value, and the government regulation says that. So, the regulation requires that alcohol content of the film should be less than 10 to minus 4. Okay. So, in order to remove the alcohol, it is proposed that to evaporate it at 125 degrees Celsius. So, to remove alcohol, it is proposed to evaporate it at 25 degrees Celsius, 125 degrees Celsius. Now, at this temperature, the chromatography experiments gives chi as 0.44 and vapor pressure of the isopropyl alcohol is 4.49 bar. Okay. So, what we need to find out is calculate the low pressure that must be maintained in the evaporator, okay, to achieve this kind of purity of the film. Now, under this condition, what is being given is condition. So, we is given that activity is given as a ratio of the partial pressure by the vapor pressure, okay, and the polymer basically is involatile. Okay, so this is a very long description of the problem. Okay, it's very straightforward. So, what we need to find out is basically the content of the alcohol should be less than 10 to minus 4 and chi value is given, the saturation pressure is given and activity is given in this ratio, and polymer is basically involatile. So, how are we going to solve that? The Flaherty-Huygens theory is already states that from here ln gamma 1 infinity, I actually considering that the gamma is greater than 1, this can be written as simply 1 plus chi. Okay. So, let me just try to solve here. So, gamma is greater than 1, indicate ln infinity is 1 plus chi, and chi is known, this is 0.44, this is, that means this is 1.44, which essentially means gamma infinity is 4.22. Okay. So, as defined, what is gamma infinity? Gamma infinity definition wise is this. Okay. So gamma 1 infinity I can write now here at these conditions A1 by phi 1, and phi 1 for our condition need to be less than or should be less than -4. So, we can contain that this is the minimum which we have to get the volume fraction. So, from here we should be able to find out A1 is equal to 4.22 into 10 to the minus 4, okay, which is nothing but P1 by P1 stat. P1 stat we know, okay, P1 stat is given as 4.49 bar, which essentially means P1 is 4.49. This turns out to be 0.0019 bar. Okay. Now, considering that the polymer is non-volatile, which essentially means P2 partial pressure of this polymer can be considered to be 0. Therefore, P is just the pressure of the evaporator can be considered as simply P1, which is 0.0019 bar. Okay. So, this is how we solve a very simple problem. Our description was much lengthier, but the problem statement or in general the problem was very straightforward. Okay. So, now I am going to describe the third problem, which will be the last problem of the this lecture. So, this is question 3. So, you have two liquids given, liquid let us say A and B, and this is the molar volume given in centimeter cube per mole, okay, is 120, this is 180, and this is solubility parameters given in J joules per centimeter cube half, this is 18 and 12. Okay. Now, what we need to find out is estimate upper critical solution temperature for a binary mixture containing non-polar A and B, okay, non-polar liquid okay. All right. So, this is the problem statement, and the considering is a non-polar liquid solution, what we can take is we can make use of regular solution theory, and if you use a regular solution equation, then we can write GE as AX1 x2 A by B x1 plus x2, where A and B are related as, if you make use of Scatchard Hildebrand expressions, this would be VA delta A minus delta B square, this will be VB delta A minus delta B square. Now, this is GE. From here we can of course get the other expressions, but let us first find out what is A and B, because we have the information of V's and delta. Okay, so what would be A? A, if I plug in the expression from the table, it turns out to be 4320 joules per mole, and for the case of B, it turns out to be 6480 joules per mole. Okay. Now, we need to find the upper critical solution temperature, and for that we need to find out the conditions, the temperature and the composition at the consolate point. So, again, so the temperature and composition at the consolate point, that is basically the upper critical solution temperature, can be found by solving this conditions of incipient inequality, or in this case we will consider equality from solving d ln A by del x A Tp, this is equal to 0, and similarly the second derivative is also equal to 0. Okay. So now, so you can get this A's, okay, because from here you can get the log of gamma, and so once you use that log on gamma, and from there you can get this activity. So basically you can obtain this log of A. So this is something which we have done for regular solution theory, okay, straightforward. So I should be able to find, so I am going to directly write the expressions which you should be able to evaluate. Okay, this is something which you can do at home. So this is the expression which comes here, 1 minus A by B, 1 by 2 A by B, 1 minus A by B, and Tc is 2xa C, 1 minus x C A. C stands for consolidate point or critical composition. So divided by R A by B okay. So now using the values of A and B, you can find of XAC, which turns out to be 0.646, and then if you plug in that value in this expression of T, you get your critical temperature or the upper critical solution temperature as 328 Kelvin. So this is something which you can check upon doing this derivation from here till here, okay, something which you can do. So this would be the end of the problem solving session, and the idea was to illustrate what kind of problem you can solve using these solution theories, and in general the approach. I hope that you get an you got some kind of understanding of the problem of this particular course, particularly the solution theories and later part of the course. Okay, so I will stop here, and I hope you have wonderful learning in this course, and you can always write to me over emails or on forum if you have some problems, something which you interest you, and if this was not covered, it's just because there are so many things to cover as far as the solution theories are concerned, and with this limited time we could only cover a limited scope, and you probably have got an idea, and you can take it from here by looking at the textbook which we are looking as a reference text. So with that, good luck, wish you all the best for the exam, and perhaps see you in the next time.